No, if we don't talk about it before the exam, we won't be tested on terpenes. This exam. Next time, you bet. Big time. All right, so lipids is a catch-all term that describes a lot of different classes of molecules with different properties. The thing that unites them all is they're all relatively nonpolar. So we're going to break lipids generally up into two categories. We're going to call one class of lipids hydrolyzable. These are lipids that can be broken into two pieces by hydrolysis reactions, usually by an enzyme, but conceptually you can think of it as like a saponification type reaction, hydrolysis of an ester. These include waxes, triglycerides, or fats and oils, and then an interesting second category of phospholipids. All of these you've probably heard about before. Then over here we have the non-hydrolyzable lipids. These are the ones that don't break up into two different pieces based on a hydrolysis reaction. These include the fat-soluble vitamins, which are A, E, D, and K. And then it also includes a class of molecules called the eicosanoids. And there are three different classes of eicosanoids. They are grouped together because they come from the same 20-carbon precursor carboxylic acid. You've heard of some of these. One is called prostaglandins, which are involved in pain and inflammation. Another are the leukotrienes. These are involved in smooth muscle contraction, especially in the lungs. And then the thromboxanes, which are involved in clotting, blood clotting. So we're not memorizing structures, but you should recognize them, and you should be able to make sensible predictions about properties of molecules based on their structure, and I'll give you some examples of that. Let's just begin with the waxes. These are the simplest of the non-hydrolyzable lipids. These are basically just esters, and they involve a long-chain carboxylic acid that is involved in an ester with a long-chain alcohol. So there are going to be two sections of a wax, a long-chain carboxylic acid, or we might call that a fatty acid, and then a long-chain alcohol. Here's an example of a wax from a sperm whale, and it involves, let's see, 2, 4, 6, 8, 10, 12, 14, 16. It's a 16-carbon carboxylic acid, so 2, 4, 6, 8, 10, 12, 14, 16. And then a 16-carbon alcohol, 2, 4, 6, 8, 10, 12, 14, 16. So in orange, pink is the carboxylic acid portion, and in orange is the alcohol portion. And waxes are found in nature in in coatings of leaves to prevent undesired transpiration, loss of water from leaves. It's also found in animals, coatings for feathers or hair to keep water out. And waxes are the easiest to recognize. They're basically hydrocarbons, except there's an ester in the middle. We don't have too much more to say about it beyond that. Let's talk now about triglycerides. This is the class of lipids that you probably have the most experience with in your day-to-day life. These are also called triacylglycerols. So triglycerides are also esters, but they are triesters between. They have a fatty acid portion, and then they also have a 3-carbon triol, that means trialcohol, which is called glycerol. So the long-chain fatty acid looks like this. We might draw one that's 16 carbons, 2, 4, 6, 8, 10, 12, 14, 16. And then glycerol is just the 3 carbon chain with alcohols on each carbon. So put together in an ester form, the triacylglycerol or the triglyceride will look like this. And I'm not going to draw the long chain fatty acid, but we'll highlight that portion in pink, and then in orange we'll highlight the glycerol portion. And as I said, these are called fatty acids, and there are going to be 3 of them per triglyceride. These can be either saturated, meaning no double bonds, or unsaturated, meaning some double bonds, or some combination of 1 or 2 of them can be saturated, 1 or 2 of them, or all 3 of them could be unsaturated. So in a triglyceride, you can mix and match fatty acids. They don't all have to be the same thing. What that means is sometimes the carbon in the middle is a stereocenter, but we won't worry about its configuration. There are enzymes called lipases that hydrolyze the ester linkage between the glycerol oxygen and the fatty acid carbonyl to liberate 3 fatty acids and 1 glycerol. We'll learn about that when we talk about metabolism. We'll learn about what's going on in the active site and how that hydrolysis reaction occurs. Our ancestors did this hydrolysis reaction to make soap. They did that with lye that they got from wood ashes, and it was just an OH minus attacking the carbonyl carbon, displacing the alcohol like you saw in chapter 16 to make fatty acids, which we'll talk about, form micelles. So triglycerides together are what we're referring to when we talk about fats and oils. I think in general, oils are derived from plants and fats are derived from animals, is sort of how we talk about it. Except for snake oil. I don't know about snake oil. I don't know that it actually refers to an actual thing. Snake oil salesperson. I just imagine someone taking a snake and sort of twisting it and snake oil dripping out or something. I hate snakes, by the way. Why did it have to be snakes? There's a kid in our ward who's really cute. I think he's 4 or 5. A couple years ago, he's like, I had a birthday party and we got to touch snakes. And they didn't even bite me. And I'm like, I can't imagine a more hellacious birthday party than if there were snakes there. That would be just a nightmare. You want to plan my horror birthday party? Yes, there should be snakes. Okay, so what we want to do now is talk about the relationship between the structure of the fatty acids, which can vary among the various kinds of fats and oils, and the overall property of the fat or oil. We're going to do this pretty quickly, just focusing in on the fatty acid portion. And the idea here is not my screen, there it is, but to understand the trends. And I think some of this should be pretty straightforward based on stuff that you learned in 351. So saturated fatty acids, we're going to list a number of carbons here, and we're going to list the melting point. Obviously, I don't want you to memorize melting points. That would be silly. But I do want you to be able to rationalize what's going on here with the various melting points. So the 12 carbon fully saturated all alkane chain has a melting point, and this is just of the fatty acid, not of the triglyceride, of 43 C. You go up to 16, it's 63 C. You go up to 18, it's almost 70 C, and you go up to 20, it's now 77 C. So you're noticing that melting point increases with number of carbons. And my question is, why? You should know that. Go ahead. Okay, van der Waals interactions explain, yeah, but why should those increase as you increase the number of carbons? Go ahead.
So the more saturated it is, the less kinks there are in the fatty acid chain, which means that they can stack better.
Okay, so we're going to talk about how introducing double bonds actually makes the melting point much lower because of stacking. Why does stacking matter for van der Waals interactions? Any thoughts there? Surface area, yeah. So van der Waals interactions are the same thing as induced dipole interactions. They improve, they are stronger with contact surface area between molecules. So larger saturated chains have more surface area. More contact surface area equals stronger van der Waals interactions. Stronger van der Waals interactions equals higher melting point. Does that make sense? I haven't written it all out there, but I think that's something you're familiar with. Yeah. Okay, now let's look at what happens when we start to bring in a little bit of unsaturation. So we're going to compare fatty acids that basically have the same length. I'm going to need a little bit more space here. Basically have the same length, but are going to incorporate one or more double bonds, unsaturated fatty acids. And here, we're going to write the number of carbons, we're going to write the number and position of the double bonds, and then I'm going to write the melting point. All right, so we'll start with 16 carbons. Your 16 carbon chain with a double bond at carbon number 9 has a melting point of 0 degrees. So that's a change of 63 degrees. That's pretty dramatic. Why aren't you gasping? There it is. That was good. That was a much better gasp than the 9 o'clock hour. I'm so impressed that you're gasping. Yeah, shocking decrease. And the idea is that the cis double bonds in the nonpolar chain creates a kink that is hard to pack into. There's steric hindrance. The chains can't get as close to each other. Lower contact surface area means weaker van der Waals interactions means much lower melting point. So the 18 carbon chain, you'll see that melting point increases relative to the 16 carbon chain that only has one double bond, but doesn't increase that much. It's only 13C. But there are this is a monounsaturated fatty acid. If we put two double bonds, one at carbon 9, one at carbon 12, the melting point drops by about 25 degrees to now below 0. And then, yeah, good. And then the 3 carbon fatty acid is still a liquid even at minus 16. And so you can see that the introduction of double bonds causes causes much lowering of the melting point. The 20 carbon fatty acid that's unsaturated actually has 4 double bonds. This one's called arachidonic acid, and it's a precursor to the eicosanoids. In fact, the term eicosanoid comes from the number 20 in Greek. This melting point is minus 50, so the 4 double bonds cause almost 130 degree change in melting temperature, and that's all because the carbon chains that have double bonds in them, cis double bonds, can't pack against each other as efficiently. So I'll just want to sort of zoom in on these 18 carbon fatty acids. And we'll draw one of them for you, but some of these have non-standard names that tend to show up. The one with just one double bond is called oleic acid. The one with 2 double bonds is called linoleic acid. The one with 3 double bonds is called linolenic acid. I'm not sure who made these up, but you'll hear those names occasionally. And then the one with 20 is called arachidonic acid, and that name will come up when we talk about prostaglandins. I'm just going to draw briefly for you the linolenic acid. This is the one with 3 double bonds. And just to show you its structure, and when you see the shape of the double bonds, you'll get the idea of how such a chain with so many double bonds would have a hard time packing closely against itself. So 1, 2, 3, 4, 5, 6, 7, 8, 9. When we get out to carbon 9, there's a double bond between 9 and 10. And its configuration is Z. And then we get 10, 11, 12. 12 and 13 have a double bond, and its configuration is Z. And then we'll get to 12, 13, 14, 15. The bond between 15 and 16 has a double bond, and its configuration is Z. And then 15, 16, 17, 18. So this is the 18 carbon linolenic acid. And again, you could see that the presence of these cis double bonds, and I'm just illustrating their shape with by filling in the hydrogens that are implied but not shown. Rotation around those double bonds is restricted. That means the molecule can't rearrange itself as efficiently to pack as tightly against other molecules, and therefore the melting point is quite a bit lower. Linolenic acid is an example of an omega-3 fatty acid. And we're going to talk about that just because people advertise to you with that word, and you should know what it means. So this is the Greek letter omega. The term omega comes from how we talk about carbon chains. You've already seen this a little bit. This is the carbonyl carbon. This is the alpha carbon. This is the beta carbon. Alpha is next to the carbonyl carbon. Beta is next to alpha, and so on. We can continue numbering out, and we'll eventually run out of letters in the Greek alphabet, and you may not know them all. I still don't. What we do is we give up for really long chains, and we start counting from the other end. And so we'll call carbon 18 at the end of the chain the omega carbon. Alpha to omega, beginning to end, first and last. Now we're getting into the scriptures. Yeah, spiritually inspiring, right? Fatty acids are spiritually inspiring. So we'll count from the end, 1, 2, and 3, and there's a double bond at the third carbon from the end. So that's why it's an omega-3 fatty acid. It has a double bond in position 3. Go ahead.
Do we need to memorize how the linolenic acid is?
You don't need to memorize the structure, but if I ask you which of these is an omega-3 fatty acid, you should be able to tell which. Yeah?
For because they're all Z double bonds.
Yep.
Would an E configuration be more stable?
Would an E configuration be more stable? Yes, and we'll get to that in a little bit. Okay, yes?
Could you go over again how that's a 3 omega fatty acid?
Yeah, so the carbon at the very end of the chain, we call it omega. Then we start numbering from that carbon, 1, 2, 3, and there's a double bond at that carbon 3. So that's why it's called omega-3. Yep. Yeah?
Are omega-3 fatty acids like a family of different kinds of acids with different kinds of double bonds later down the line?
Are omega-3 fatty acids a family? Do they have different kinds of double bonds? Well, if you look at these 18 carbon chains, oleic and linoleic would not be omega fatty acids because they only have the double bonds at 9 and 12 and not at 15. Yep. Now, people advertise to you there are purported health benefits to omega-3 fatty acids, as there are for a lot of unsaturated or fats and oils that contain lots of unsaturated fatty acids. They're purported to have some cardiovascular benefits. We'll talk about those in just a little bit. I'm not a physician, I'm not a nutritionist, so my knowledge on that is just not very good. So I'll tell you what little I do know, and then you can await further instruction in that area in the future as you take other classes. I will say that you've been advertised to eggs in particular that are rich in omega-3 fatty acids. I used to think, what are they doing, engineering the chickens so that they produce more omega-3s? No, they're just feeding the chickens a lot of omega-3 fatty acids, and then they just put a lot of omega-3s in their eggs. Yeah?
Do they use that naming for more than just the linolenic? Like for the linoleic, would you call that an omega-6 fatty acid?
Could you call that an omega-6 fatty acid? Yes, I suppose. I haven't heard of that. The only thing I've ever heard is omega-3, but that would make sense. Okay. All right, so yeah, let's now talk about, we're going to come back to the idea of trans fats and unsaturated and saturated fats. But before we do that, I want to take what you've learned here about melting points, and then we're going to look at some triglycerides that are actually in products that you may have bought. So what we're going to do for various fats and oils is I'm going to write down the composition, and the numbers here are percentages, though they don't add up to 100 because I'm only showing you some of the saturated versus unsaturated fatty acids that are present in these fats and oils. So along with the saturated fatty acids, we're going to go 12, 14. Actually, erase the 12 because it's not even going to be numbers. Our numbers are going to be from 14 to 16 to 18. And then on the unsaturated side, what we're going to talk about mostly are 18 carbon monounsaturated and 18 carbon diunsaturated. So this would be oleic and linoleic acids. And then we're going to just do various, the numbers here are number of carbons. And I guess I didn't need to run out of space that much. There we go. Now the table is prettier, there we go. So various types of fats. So animal fat is one of these. This may be marketed to you as tallow or lard, or the more exciting name, manteca. I served my mission in South Texas in the Rio Grande Valley, and you talk to people in English or in Spanish that mission. We were all Spanish speaking plus English speaking, but our gospel Spanish was pretty good. Our walking around town and asking where the grocery store is Spanish was not that great. Donde está la H-E-B? H-E-B is the store, the chain in South Texas, right? And I remember, right, in some places the laundromat was called the washateria, which is really kind of fun, terrible Spanish, but you could buy lard or manteca in H-E-B. It was in these 5-gallon buckets like you get at Home Depot, only it was full, and it was full of animal fat. Big yellow buckets with red lids, manteca on the side. And you know what they used that for? Tamales. Tamales, such good tamales when made with actual lard. Now, as you know, lard is solid. So let's look at the components of animal fat. It's about 1%. About 1% of its triglycerides have at least. Well, if you hydrolyze the animal fat and analyze the fatty acids, about 1% is a 14-carbon chain. About 25% is the saturated 16-carbon chain. About 15% is the saturated 18-carbon chain. About 50% is the monounsaturated, and about 6% is the diunsaturated. And yes, I know those numbers don't add up to 100. There's other components that I'm not writing down. So you can see that you don't need a huge amount of unsaturated fatty acids for something to be a solid. Okay? In contrast, if we look at olive oil, it's got a much smaller amount of saturated fatty acids. It's about 80% oleic acid and about 7% linoleic acid. And of course, olive oil is, as you know, a liquid. So you can see that incorporation of at least a substantial percentage of saturated fatty acids makes the triglyceride a solid. Peanut oil, here's an interesting one. It's about the same as olive oil in terms of its saturated composition, but peanut oil has more of the diunsaturated fats. And a lot of nuts have more polyunsaturated fats in them than just like olive oil does. We'll talk about peanut oil in a minute. Coconut oil is called an oil because it's from a plant. It's only 7% monounsaturated, and I don't have the specific breakdown, but overall, coconut oil, I think including a 12-carbon fatty acid, is about 86% saturated. You go buy coconut oil, it's not a liquid, or it might be, but not at room temperature. It's just in a jar and it looks white. If you heat it up, it'll melt and you can pour it. One of my sons likes to put it in his hair, but then if he goes outside and it's cold, it sort of freezes on his hair. It gets crinkly. It's kind of interesting. But and again, it's a solid at room temperature because it's large composition in saturated fatty acids. Okay, so let me ask you a question. If you go to the store and you want to buy peanut butter and you've been marketed to and influenced and you have this idea that if you buy all natural organic peanut butter, it's better for you, and so you find the jar of Adams or whatever it is and it's got liquid on top. What is that liquid? It's the peanut oil, okay? All right, and as you know, peanut oil is a liquid. So you have some choices there. You can slurp that stuff off the top and then somebody at 9 o'clock said, extra credit? And I'm like, knock yourself out, kid, but I'm not paying for that. Or you can stir it up and mix the oil in, and then you can spread the stuff out. But you're going to have to do it again and again every time you open the jar because the oil separates out. It's a liquid and the solids sink to the bottom. Okay, good. So when you buy Skippy, it doesn't have the delicious oil juice at the top, so why not? What have they done? Go ahead. They hydrogenated it, yeah. So let's talk about why they might hydrogenate it. We'll do this as an example with linolenic acid, which you've seen is a major component of, well, all right, we'll do it with, this was linolenic. We need to make it linoleic so it can be in peanut oil. So we'll get rid of that double bond at 15. So what happens with hydrogenation? This is just, you've seen that label. Actually, if you turn this jar of Skippy around, it will say hydrogenated vegetable oil or soybean oil or something. All they've done is they've passed that oil over a palladium catalyst with hydrogen. That's called hydrogenation. You learn that reaction in 351, and what that does is it reduces the alkenes to alkanes. It gets rid, that's an A there, sorry, anes. That gets rid of the double bond. So that would make the 18 carbon saturated fatty acid, which we don't need to draw because you can imagine it. You could draw it if you needed to. That's going to have a higher, much higher melting point. In fact, we know what it is. It's around 70 degrees for the 18 carbon saturated fatty acid. For linoleic acid, it's minus 12. So, and you can expect the triglyceride melting point that is composed of mostly those to follow that trend with the fatty acid pretty well. So you hydrogenate it, now it's solid, and it doesn't separate out on top, which makes consumers less grossed out. Yeah, go ahead.
Does it also get the carbonyl?
It doesn't get the carbonyl. So you can reduce carbonyls with palladium. You learned that reaction in 351. But carbonyls, because oxygen's more electronegative than carbon, carbon-oxygen pi bonds are way more stable than carbon pi bonds, and so it's tougher to hydrogenate them, so you can do it selectively. Yeah. Okay. So there's, aside from the gross out factor, no, you don't want the peanut, you don't want the oil at the top of your peanut butter. There is another reason why people hydrogenate fats and oils, and the reason is shelf stability. So you need to know something about this when it comes to fats and oils because it affects your day-to-day life and some of the shopping choices that you make. So one thing that you learned in 351 is that double bonds are nucleophiles. Pi bonds are nucleophiles. They can attack electrophiles. And also, double bonds are, how do I say this? They are prone to radical reactions. You learned this at the end of 351 when you looked at chapter 22, and you discovered that carbon CH bonds that are adjacent to pi bonds are subject to radical type reactions. Let me show you an example of that. So this carbon, let's see, 9, 10, 11. Carbon 11 is what we would call an allylic carbon, meaning it is adjacent to a double bond. And in fact, it is doubly allylic because it's between the pi bond between 9 and 10 and the pi bond between 12 and 13. Now, the atmosphere that we live in has lots of oxygen in it, and though you've drawn oxygen in a different way before, you can think of it as being mostly a diradical. You've drawn oxygen with a pi bond in it, but if you do the MO picture of oxygen, even though there are 2 pi bonds, there's also 2 unpaired electrons. So you can think of oxygen as a diradical, which is why it's sort of a problem. And oxygen can, I mean, this is how fires get started too, but one of the things that happens is one of the radicals on oxygen can abstract a hydrogen atom from C11 of linolenic acid or linoleic acid, either one. And the reason it can is because that CH bond is weak. That CH bond is weak because the resulting radical is stabilized by resonance. So if I draw the thing that's left behind after we abstract that proton, that hydrogen atom, you've got over here the new bond between oxygen and hydrogen, and then over here you've got the radical left on carbon 11. And I'm not going to draw the resonance structure, but you can imagine you can stabilize radicals in the same way that you can stabilize carbocations. That radical could end up on this carbon or that carbon. So the fact that you've got allylic carbons makes unsaturated fatty acids subject to oxidation. One of the many things that can happen after this radical step is that the radical on carbon 11 can recombine with the peroxy radical that we just made to generate what's called a peroxide, an organic peroxide, where we're going to have, a new carbon-oxygen bond on carbon 11. So that's an oxidized fatty acid. And if that's done in the context of a triglyceride, the fatty acid doesn't taste very good. In fact, it starts to taste bad and smell bad. We call that rancidity. It's the weird taste that happens when unsaturated oils get oxidized. Some of you maybe spent a couple of years wandering around hot climates with a vial of olive oil, consecrated oil in your pocket for the whole time. Maybe you used some of it, maybe you didn't have a chance to. You come back, you open it up, you smell it, and it's nasty. And the reason it smells nasty is because it's gone rancid, it's oxidized. You've made a ton of peroxides. That affects flavor, that affects taste. I don't think the General Handbook of Instructions has any commentary about how much oxidation is necessary before consecrated oil becomes unconsecrated, but if it stinks, you ought to replace it, okay? It's not that hard. So anyway, and this allows me to tell you a story of why my mom thinks I can't handle difficult cooking instructions. I'm 45 years old, but we go to my mom's house, mom and dad's house, every couple of weeks for Sunday dinner. The kids love it. They call it Grammy Sunday. And we share food assignments, but my mom has limited confidence in my ability to carry out a food assignment. So we normally get assignments like, just bring a salad. Okay, I'm going to cut some lettuce. I'm good at that. One time we were going to have tostadas, so I needed to bring the tostada shells. That was my one job. I had one job. Tostada shells are made, of course, with corn flour and other things, and vegetable oil, which, as you know, goes rancid. And we don't eat tostadas a lot, and I thought, we don't need to buy any. I have some in the pantry. They're great. So I pulled those out, and we went to the dinner. We started eating, and there's something wrong with these tostada shells. And it turns out they were expired by a couple of years. So shelf stability, right? If they had just used saturated fats to make those, if they had used the manteca, if they'd used the good stuff, probably they wouldn't have expired quite as quickly because the unsaturated triglycerides in my tostada shells went rancid and they were disgusting. So my mom rightly does have limited confidence in my ability to carry out cooking instructions. So one of the reasons they hydrogenate is to get rid of the double bonds. No double bonds, no oxidation, shelf stability, right? But there's a potential drawback, two potential drawbacks to to hydrogenation. The first is, as you know, saturated fats are associated with negative cardiovascular outcomes. Now, it's tempting to think that it's all about melting point, that if you eat oils that are solids, well, the solid stuff's going to clog your arteries more than the liquid stuff does. That's not actually what's going on, and the story's more complicated than that. I don't understand it very well, other than to say that there's evidence that unsaturated fats promote uptake of LDL particles in your liver. LDL particles are low-density lipoprotein particles. They remove cholesterol from your blood, and so unsaturated fatty acids promote lowering of cholesterol blood levels. higher saturated fats go the other way and promote increasing of your LDL particles and increasing of cholesterol in your blood. And it's cholesterol being carried by LDL particles in your blood that leads to plaque formation and negative cardiovascular outcomes. I have no idea about the mechanism or the epidemiology. You're probably going to learn about that at some point in the future, but that's one reason that's one reason why hydrogenating the snot out of everything just because of shelf stability is maybe bad, right? And so American consumers slowly started to get educated to this. When I was a kid, crackers were all fully hydrogenated with saturated fats, but as American consumers became educated, companies started stopping doing that and just using regular normal oils that have some unsaturated fats, but shelf stability suffered there. And so to this day, things are going to expire, especially if they're non-hydrogenated oils. The other problem with hydrogenation is if you don't do it completely, in particular if something says partially hydrogenated, that means they hydrogenated some but not all of the double bonds. The incomplete hydrogenation is sort of a reversible process. Double bonds can get reduced to alkanes and then reoxidized. And when that happens, you get some isomerization to trans. And that's where the idea of trans fats come from. You get cis-trans isomerization, and now you have unsaturated fats, but they're not cis, they're trans, and their melting temperatures are higher now because trans double bonds can pack more tightly. And trans fats are also associated with negative cardiovascular outcomes for reasons I don't understand. So, again, American consumers got a little smarter, and marketers got even smarter than American consumers, and they have this idea trans fats are bad, so now they start advertising products to you trans fat free, which of course it's going to be trans fat free if it hasn't been hydrogenated. All oils and fats are originally trans fat free. That's how they're made. Trans double bonds are not present in natural fats and oils. So if somebody tries to sell you a bottle of olive oil and tells you it's trans fat free, they're trying to, it's probably more expensive than the other bottle of olive oil, which is also trans fat free. So be a wise consumer. The other thing you should realize is just because a product says trans fat free doesn't mean there are 0 grams of trans fat in it. The FDA allows you to say trans fat free when there's like less than a threshold amount. I forget what it is. Somebody might know it. It's like 500 milligrams, half a gram or something like that. So, all right. Okay, I think we've done what we needed to there on triglycerides. Let's talk about phospholipids. So phospholipids are closely related to triglycerides. You will see that they have the same basic structure. Only one of the esters of the triglyceride has been hydrolyzed and replaced with something else. So a phospholipid will have 2 long-chain fatty acids. I'm just going to color these pink the way we've done previously. These can be either saturated or unsaturated. The more unsaturated fatty acids are in the phospholipid, the more fluid the membrane that the phospholipid makes will be. And then the other oxygen is tied up, maybe I'll draw it in this direction, is tied up as a phosphoester. So this kind of bond between an oxygen of an alcohol and a phosphate group, that kind of bond is called a phosphoester. And then what's over here on the other side varies depending on the identity of the phospholipid. So for example, if that R group is just a negatively charged oxygen, that molecule, that phospholipid, is called phosphatidic acid. And bacterial membranes are made mostly of phosphatidic acid. And as you can see, that means that the membrane is anionic, meaning negatively charged. It already has one negative charge there, and if this R prime group is O minus, then the phospholipid head group is doubly negatively charged. Okay, so this is going to be the polar head group, and then the nonpolar tails are the fatty acids. Each of these polar head groups that we're going to talk about are soluble in water, but you're going to see they're going to vary in their charge. And this is where we get selectivity among antimicrobial peptides for bacterial cells versus your cells. Remember, we learned in our chapter on peptides and proteins that antimicrobial peptides are cationic. They're positively charged. They get attracted to bacterial membranes because bacterial membranes have a large composition of phosphatidic acid and are mostly negatively charged. There are other groups that can be attached to that phosphorus. For example, if the oxygen is from another alcohol, this alcohol is called ethanolamine. It's got at physiological pH, that amine is positively charged. This lipid is called phosphatidyl ethanolamine. And as you can see, this lipid should be, this was a term the 9 a.m. kids had never heard before, zwitterionic. You've heard that term before? Now you feel smarter than the 9 a.m. kids. Good, all right. It's okay if you've never heard it before. Actually, it means a molecule that's neutral because it's got a plus and a minus in the same molecule. So in phosphatidyl ethanolamine, the minus is here in the attached to the phosphorus. The plus is on the ethanolamine group. And this is abbreviated as PE among lipid people. A lot of eukaryotic lipid membranes are composed mostly of zwitterionic lipids. So if you take the ethanolamine and you modify the nitrogen with methyl groups so that it's positively charged, it's a quaternary ammonium ion, that 2-carbon amino alcohol is called choline, and the lipid that's formed from it is, there's an S in there, phosphatidyl choline, or PC, and it is also zwitterionic. And then another one that you ought to know is called PS. That's if the alcohol attached to the phosphorus is serine, an amino acid, instead of just the 2-carbon amino alcohol. So here is the oxygen of the serine side chain. Here's the alpha carbon, here's the backbone ammonium group and the backbone carboxylate, alpha carbon, beta carbon. This is the serine side chain. And this lipid is also anionic because overall, 2 negative charges, 1 positive charge. So lipid membranes are composed of these phospholipids, and they differ, again, in the amount of each type of one. There may be any of these types of phospholipids found in any particular membrane. Different tissues, different organisms will have different compositions of phospholipids. One other one that we should cover here, it's not based, it falls into the class of phospholipids, but it's not based on glycerol. So this particular lipid is called sphingomyelin. And I don't want you to memorize its structure, but I do want you to recognize it as distinct from from the other phospholipids that are based on glycerol. So yeah, the key point you need to remember here is it's not glycerol based. So its structure is kind of weird. We'll draw it here for you. It starts with an OH group, and then a trans double bond, and then on the other side of that trans double bond are 13 carbons. So let me make sure that's true. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yep. So starting here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, then there is a bond here that should be a wedge because it's going to a stereocenter. I don't like how I drew that. There we go. That should be longer. More space. All right, then there's a nitrogen here, and that nitrogen is tied up in an amide bond with a 14 carbon chain. So 2, 4, 6, 8, 10, 12, 14. Then there's an oxygen here. That oxygen is bonded to a phosphorus. And then that phosphorus is bonded to ethanolamine. So you can see how sphingomyelin is similar to phosphatidylethanolamin. It is also a Zwitter-ionic lipid. It's also got a polar head group, and it's also got two nonpolar tails. Only the nonpolar tails, only one of them is a fatty acid. You can hydrolyze this amide bond, so sphingomyelins fit into the category of hydrolyzable lipids, and they share the same basic structure with the other phospholipids of a polar head group and then two nonpolar tails. Again, I'm not really caring that if I draw a molecule, I say which one is phosphatidylcholine. I don't know that it's that valuable for you at this stage to know the difference between choline and ethanolamine. I could ask you which of these lipids is Zwitter-ionic. That would be a pretty easy question because all you got to do is count the charges. And I could ask you which of these is a sphingomyelin, and you just need to recognize the one that's different, the one that's not based on glycerol. Yeah?
We need to memorize the structure of the groups or like.
Of what? Of the head groups? No. But you should be able to answer questions about them if the structures are given to you. Yeah?
Does sphingomyelin have anything to do with myelin?
Yeah, so the myelin sheaths that surround neurons, their membranes are particularly rich in sphingomyelin. Yeah?
Show me the glycerol, like what part of the phospholipid is the glycerol that's not?
Yeah, so the glycerol is this 3-carbon alcohol, this 3-carbon chain that has 3 oxygens on it. Whereas in sphingomyelin, there's sort of a 3-carbon thing, but it continues on without an oxygen into that upper chain. Okay. So, yeah, go ahead.
Is that molecule specifically sphingomyelin, or is that more than
That's a great question, and I don't know the answer to it. I think this molecule is specifically called a sphingomyelin, but I think you can probably vary the head group. I just don't know. Yeah. All right. In the last little bit, I want to show you just briefly what phospholipids do. So we're going to envision both phospholipids and sphingomyelins as having a polar head group like this, and then 2 nonpolar tails, which I will illustrate just with a gray squiggly line. And of course, sphingomyelins, so this would be the typical phospholipids based on glycerol. We call them diacylglycerols, and then this would be sphingomyelins. If you sort of zoom out and squint your eyes a little bit, you can see the similarity between the two of them. They both have 2 nonpolar tails. It's just in the case of sphingomyelin, one of the tails is a little bit different from the others. Both of these have a particular shape. If you allow them to wiggle around in solution, they adopt sort of a cylindrical shape. And I forget whether we've talked about this before, maybe we have. But if you put these types of cylindrical shaped phospholipids, the diacylglycerols and the sphingomyelins, in water, the hydrophobic effect causes them to associate together side to side with the polar head groups close to each other and the nonpolar tails next to each other. Now I realize you can't do this if you're writing with pen and paper, and you don't need to, but over time you can get side-by-side association, and because they're cylindrically shaped, there's not a lot of curvature. What that means is you've got a layer of molecules that's polar on one side and nonpolar on the other. Now, at a certain concentration, there's only enough to form a monolayer, and what will happen is the polar head groups in water are going to be exposed to water, but they're going to stick their nonpolar tails out into the air because it's better to be in air than it is to be in water. But as concentration increases, it actually becomes favorable to form a bilayer in which the nonpolar tails interact with each other, sequester each other from water, and then you have water inside and outside this bilayer. We'll talk about that just a little bit more on Monday. Have a great spring day, and I'll see you Monday.